last two classes, we have looked at arrays, talking about vectors and matrices. So today we continue from where we left, and we start looking at array calculations. In MATLAB, there are two types of arithmetic operations that can be carried out on array, what we call array. The first one is the matrix arithmetic operation, and the second one is the array arithmetic operation. For the addition and subtraction operation in MATLAB on arrays, the symbol is the same. So when you want to add or when you want to subtract, you use the typical symbols that we use for arithmetic addition and subtractions on the elements of the array. However, when multiplication, exponentation, division has to be done on an array, you have to be sure that the dimensions are compatible before you know which of the operators to use. Now, if you be carrying out matrix multiplication or division or exponentation, the symbol is as displayed on the screen. If the arithmetic operation you are going to be carrying out is array arithmetic operation, it has to include dot. The typical multiplication symbol that we use to carry out arithmetic operation will not suffice if it's going to be an array arithmetic operation. You have to include a dot that precedes the asterisk that is used for multiplication. Likewise, for division, you have to put a dot before the forward slash. And we also have what is called the left division, or what we call the back slash. You have to precede it with a dot if you are carrying out array arithmetic operation. If it's exponentation also, which is an array exponentation, you have to put the dot before the caret sign. So the next thing is, what's the difference between matrix arithmetic operation and array arithmetic operation? Now let's start with the addition operation. Now let's say you have a scalar that you want to add to an array. By writing the plus sign and adding the scalar to the array that you have, what happens is that each of the elements of that array experiences the addition of that scalar that you are introducing. For example, we have here a vector named x that has elements 1, 2, 3. So if you add 2 to the vector x, what happens is that each of the elements of vector s has an increment of 2. So it's element y. So that is one reason why there is no difference between addition for matrix operation or array arithmetic operation. Okay, when you have two same sized array, so you could say array A plus array B, or you could say array B plus array A. It wouldn't matter if B comes before A or if A comes before B. The only thing that is important is that for this addition operation to be carried out, the arrays must be of the same size. Okay, so now before we move into that, let's add the scalar to the variable x, which is an array that contains elements 1, 2, 3. So let's create the variable x. Okay, now that we have this, let's now add a scalar which is 2 to create a variable y. Let's add 2 to x. So we realize that each of the elements has increased by 2, that is added to x. Now we have said that we could add two arrays together, and what happens is that each of the corresponding element in the two same sized arrays will get added together. So we could create a variable z from x and y that we have just created. So what we observe here is that the corresponding element in x has been added to the corresponding element in y. The most important thing here is that the two vectors, the two arrays that we are adding together, are of the same size. It wouldn't matter if we are written z is equal to y plus x. So that's one of the reasons why for additions operation we don't need to put dots or be concerned about the dots when we are carrying out that operation. The same thing goes for subtraction. It doesn't matter, because eventually what will happen is that the operation will be carried out element wise. So for array arithmetic operations, the operation is actually carried out element wise. So the changes is peculiar to each of the elements in the array. Okay, let's look at something like multiplication. If you are multiplying an array with a scalar, it wouldn't matter if you specify that this is an array arithmetic operation, because since it's a scalar, that scalar will multiply each of the elements in the array element wise. So in that kind of a scenario, you don't need to specify the dot. So let's see an example. Let's say this is z, and z is equal to 2 multiplied by x. So it gives us result even without the dot symbol. The same thing if you are dividing with a scalar, you don't need to include the dot before you can get an answer. So let's see an example. Let's say y equals to 3x divided by 3. So because one of the operands is a scalar, we don't need to put dot in the operator. However, when you want to multiply two equally sized vectors, you cannot use the asterisk sign just like that. This is because the asterisk sign, as you have seen in the previous slide, is matrix arithmetic operation, and that requires that the number of column in the first array should be equal to the number of row in the second array. So here, number one, when you are carrying out matrix arithmetic operation, arrangement of the array matters. It matters which of the array comes first, which of the array comes next, because it is essential that the number of columns in the first array equals to the number of rows in the second array. So when that is not equal, you cannot carry out matrix multiplication. So when we look at two equally sized vectors, so let's say we have a 2 by 1 vector. So it means that the number of row is 2, the number of column is 1. If you try to use matrix multiplication on that, you are going to get an error, because obviously the number of rows in the second array is not equal to the number of column in the first array. So let's try and see if we can multiply equally sized vectors just using the asterisk sign alone. I expect that we should get an error message. So let's attempt to create a variable z, which is the matrix multiplication of a 1 by 2 matrices. So if you attempt this, as expected, an error message was given to us that we have an incorrect dimension for matrix multiplication. Okay. Now, instead of using matrix multiplication, if we had used an array multiplication, then we have outcomes. So instead of using asterisk alone, let's precede the asterisk with a dot, which indicates that we are carrying out array multiplication. So let's fetch the command that we had before. So we have fetched z. So now let's introduce dot before the asterisk, indicating that we are carrying out array multiplication. So this gives us an outcome. So what has happened here? Each element, corresponding element of the two arrays have multiplied each other. 3 is the first element in the first array, 10 is the first element in the second array, so they have multiplied each other. 4 is the second element in the first array, 20 is the second element in the second array. They have multiplied each other and we have a result. So for array operation, it is done element wise. So we have some examples that you can try to reinforce the learning. Now you can have an array raised to any power if that array is square. If it's a square matrix, something like a 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, and so on and so forth. So raising an array to a power is possible if and only if that array is square. But if it's not a square matrix, if it's not a square array, what you can do is to carry out an exponentiation that is an array exponentiation. What do I mean? You need to put a dot before the caret sign. So let's see the difference between the two. So let's create another array A that has the first row, the member of the first row to be 1 and 2, and the member of the second row to be 3 and 4. Let's create that array first. So now that we have the array, so let's say this is a 2 by 2 array, so it is a square matrix. So it's possible for us to get that array raised to power any power. So now let's try and raise that array raised to power 2. That is, that array is multiplying itself 2 times. So we expect this to give us result because it is a square matrix. So the outcome is 7, 10, 15, 22. So that is the outcome of the matrix exponentiation. So if we carry out array exponentiation, let's see what happens. Let's see what the outcome looks like. So this is the command for array exponentiation. So we discover that each of the elements of array A has been raised to a power of 2. So those are the differences between the outcomes of matrix arithmetic operation and array arithmetic operation. In MATLAB, there are special matrices that you can explore. So now that you are aware that there are special matrices that you can explore, it can be handy for you as you progress in your engineering journey. So you could look up how this matrices works and how you can implement them. But before we move to the next thing, let's look at the magic function. Let's see how it works. So for the magic function, it creates a magic square matrix, and we expect that the sum of the elements in each of the row will equal to the sum of the elements in each of the column, and it will equal to the sum of the elements at the diagonal, in as much as n is greater than 2. What do I mean by n? N is the size of the square matrix you are trying to create. So anything from n equals to 3 and above, you are going to get a square matrix that has the sum of the element on its row, the column and diagonal to be equal. So what can we expect it to be equal to? It's going to be equal to n into n squared plus 1 bracket close divided by 2. So that's the value that the constant is going to be. For example, if n equals to 3, we can expect that the sum of the element in the row, the column, the diagonal equals to 3 squared plus 1, which is 9, times 3 squared plus 1, that's 10. 10 divided by 2, that should be 5, and 5 times 3 should give us 15. So we can expect that the sum is going to be 15. If n were to be 4, we should get the result that is 4 squared plus 1, that's 17, times 4 divided by 2, so that's 34. So and so on and so forth. So that's how to predict what the sum of the resulting element is going to be. So let's try and create one. Let's create a matrix that has the sum of the elements in the row, the column and diagonal equals to 34. So as we have just explained, you see that n should be 4. So in that wise, we say magic is the name of the function, then you open a parenthesis and pass in the argument. So this time around, since you are creating a magic matrix, a matrix that has the sum equals to 4 across the diagonal, the row and the columns, then n should be 4. So let's see the output. So if you find the sum across the row, the column and the diagonal, we'll discover that it is actually equals to 34. Let's pick the first row for example. 16 plus 13, that's 29. 29 plus 2, that's 31. 31 plus 3, that's 34. So you can do the same thing for each of the rows, each of the column, and also the diagonal to confirm that. And you can also explore more values of n to reinforce what we have just showed. Now we move on to application of matrices. Now we've been able to create matrices, we've seen how to edit matrices, we've seen how to create vectors and all of that. We've seen how to concatenate. So now let's see how can we apply some of the things that we have learned so far. Now the equation that is on the screen is the typical way of representing a linear set of equations, simultaneous equations. And to solve this problem using matrix approach according to some of the mathematical courses that you have done before, for example your CHE334-MATLAB-ARRAY-WEEK, you will need to create a coefficient matrix Now we have named our coefficient matrix as capital letter A, and the elements is as seen on the screen. Then also you will need to generate the variable matrix, and in this case our variables are x1, x2, x3, and you see the way the variables have been arranged. The first variables are in what we call column 1 from the equation, x2 in what we can call the second segment, and x3 is in a place where we can call the third segment. So that forms the order in which you are going to create the column matrix for the variable matrix. So the order was x1 before x2 before x3, so that's why it is appearing that way in the column matrix for the variable matrix. Also, you are going to create the constant matrix, and the values are going to be arranged in the column matrix according to the way the equations have been written, because the way the equation have been written forms the way we have constructed the coefficient matrix. So we will be following that same order so that we have the correct data set to work with. Now, when the coefficient matrix, the variable matrix, and the constant matrix have been created, to solve that or to represent that equation, we say that the matrix multiplication of matrix A and X equals to matrix B. Now X in this case is the variable we are to solve for. So to get X, the answer is going to be A inverse matrix multiplication B. The arrangement is very key, because for matrix operation, matrix multiplication, the order is very important, because we already said the number of columns in the first array should equal to the numbers of rows in the second array. So it is this arrangement A inverse B that can satisfy that compatibility requirement for matrix multiplication. That being said, in MATLAB, there are typically two ways to solve for X. The first one is to use the matrix inverse function represented by INV. Another one is to use the backslash operator. The backslash operator has abstracted the process that is involved in the Gaussian elimination technique. So once you use the backslash operator, it's going to give you an answer which is as a result of the abstraction of the Gaussian elimination method that can be used for solving matrix problems. So let's apply this information to this set of equation. The first thing is that we need to create a coefficient matrix, we create a constant matrix, and in the order that the variable has appeared, we construct a column matrix in that same order. So here, for the first row of the coefficient matrix, the elements are going to be 1, 2, 3. On the second row, the elements are going to be 4, 5, 6. On the third row, the elements are going to be 7, 8, and 0, because there is no term that has Z in the third row. For the constant matrix, the first row is going to be 1, the second row is going to be 1, the third row is going to be 1. For the variable matrix, the first column is going to be X, the second column is going to be Y, the third column is going to be Z. So when we eventually apply maybe inverse function or the backslash operator, it will imply that the first value we get will be the value of x, the second value we get will be the value of y, and the third value will be the value of z. So based on our understanding of how matrix is presented to MATLAB, let's create matrix A, matrix B, and get the value of x. So row 1 has 1, 2, and 3 for matrix A. Row 2 is 4, 5, and 6. Row 3 is 7, 8, and 0. So we could remove the semicolon so that we can see what it looks like. So we have our matrix A and our matrix B. Matrix B has 1 in each of the rows. So let's try the inverse function first to get the value of our variables. So let's name the variable as capital letter X here, and each of the elements will correspond to small x, small y, and z as given by the equation we are solving. Okay, so from the rule, it's A inverse matrix multiplication B. So the inverse function, like I said earlier, is INV. We open parentheses, supply the argument, and the argument in this case is array A or matrix A. So let's get the solution. So the order is small x is equals to -1, y equals to 1, and z equals to 0. So let's try the Gaussian elimination technique. So we still have our A, we have our B. We don't need to recreate that. But to be able to differentiate between the first answer we got and the next answer that we get, so let's name the variable we are looking for. Let's name it S this time around, and we expect that the value of x should be equal to the value of s. So for the Gaussian elimination technique, we said we'll be saying A backslash B. So it gives us the same solution. What would have spent minutes solving if we were to solve manually? By using these functions in MATLAB, we have been able to solve in a matter of minutes. Aside from the backslash and the inverse function, there are other functions that are used with matrices. One of it is the det function. What it does is that it gets the determinant of a matrix for us. For example, we might determine to find the determinant of matrix A that we have created. So to do that, we just say det. We call det as a function, and we pass in the argument, in this case, which is A. So it's returned 27 for us. This can be confirmed by manual computation. So these are some of the functions that you could use for matrix operations. So let's try to apply the determinant function to solve a set of linear equation. So let's say we have this set of linear equation as displayed on the screen. This time around we have used x, y, and z as the unknown or the variables. We have b1, b2, b3, just as the equations are arranged. b1 corresponding to the coefficient of the first equation, b2 corresponding to the coefficient of the second equation, b3 corresponding to the coefficient of the third equation. So we have created a constant matrix called B in that order, which is a column matrix, b1, b2, b3 as the element. And in that same order that the variables have been presented in the equation, we have created a variable matrix, which is a column matrix with element x, y, and z in that order. And we have created the coefficient matrix as seen on the screen. Okay, so to use the determinant method, it involves using the Cramer's rule, and that says that the solution for the first variable, just as the way they have appeared, is equal to the ratio or the quotient of the determinant that is obtained using the first column of the coefficient matrix. When you replace, it involves you replacing the first column of the coefficient matrix with the constant matrix, element of the constant matrix. So you find the determinant of that matrix that you have created as such, and you divide it with the determinant of the coefficient matrix. Then when we move to the second variable, in this case y, okay, to obtain that, we get the constant, the element of the constant matrix, and use it to replace the element of the second column of the coefficient matrix. We obtain the determinant and divide it by the determinant of the original coefficient matrix. Moving to the next variable, in this case which is z, we still need to get the element of the constant matrix and use it to replace the element of the third column of the coefficient matrix and get the determinant. Once we get the determinant, then we divide it by the determinant of the original coefficient matrix. So that is how the Cramer's rule works. So now what you will need to do is to create the coefficient matrix of the system of equation you are handling. You create the constant matrix of that same set of equation, then you create the variable matrix according to how the equation appears. After that, you get to create another matrix that has the first column of the original coefficient matrix replaced by the element of the determinant of the constant matrix. You create that. Also, you move to the next column, you create another matrix that has the element of the original coefficient matrix of the second column replaced by the element of the constant matrix. Then you move to the next column of the original coefficient matrix. You replace it. In this case, for z, it's going to be the third column. You replace that column, the third column, with the elements of the constant matrix. Once you have those newly created matrices, you get their determinants. Once you get their determinant, then the next thing is to divide each of it by the determinant of the original coefficient matrix, and with that you have your solution. So let's look at this set of equation. So the members of the coefficient matrix for this problem is going to be, for the first row is going to be 3, 2, minus 1. For the second row, the members are going to be 2, minus 1, minus 3. For the third row, the members are going to be 1, 3, minus 2. Now for the constant matrix, the elements are going to be on the first row 2, on the second row 13, on the third row 1. And for the variable matrix, the order is going to be row 1x, row 2y, row 3z. So which means the solution that we eventually obtain will be the solution of x, y, and z. Okay. So now that that has been said, to be able to get the solution, then that means we need to create a matrix that is relevant to x, a matrix that is relevant to y, a matrix that is relevant to the solution for z. So for the matrix that is relevant to the solution of x, what we need to do is that we fetch the coefficient matrix that we have named V in this case, and we replace the first column with the element of the constant matrix that we have named C here. So that means the relevant matrix, I have named it C underscore x. You can feel free to name it any valid name. So that means the member of C underscore x in this case will be 2, 2, minus 1, 13, minus 1, minus 3, 1, 3, minus 2. For the matrix that is relevant to getting the solution of y, the matrix, we are going to generate it by replacing the elements of the second column of the coefficient matrix with the element of the constant matrix. So that means C underscore y in this case is 3, 2, minus 1, semicolon. The next row we have 2, 13, minus 3. And on the third row we have 1, 1, minus 2. For the matrix that is relevant to the solution of z, I call that C underscore z, and it is equal to 3, 2, 2 for the first row, 2, minus 1, 13 for the second row, and 1, 3, 1 for the last row. How do we obtain this? We looked at the third column, since z is the third variable, and we replace the element of the third column of the initial coefficient matrix. We replaced it with the element of the constant matrix. So now that we have this, then we proceed to the stage of getting the determinant and finding the quotient of the determinant as applied. Okay, so to get x, we just need to get the determinant of the matrix C underscore x and divide it with the determinant of matrix V, matrix V. Okay, so let's look at this set of equation and apply that solution to it. So the problem says we have this set of linear equation: x plus 2y plus 3z equals to 1, 4x plus 5y plus 6z equals to 1, 7x plus 8y equals to 1. So let's solve that. Oh, okay, this was the equation we were solving. So let's get the solution to this. So let's create the variable v first, which is our coefficient matrix here. Okay. So let me correct the typo there. So this is 3, 2, minus 1. We have 2 minus 1 minus 3. We have 1, 3, and minus 2. So this gives us the coefficient matrix 3, 2, minus 1, 2, minus 1, minus 3, 1 plus 3, minus 2. So let's create the constant matrix. So we call this C this time around. So the elements are 2, 13, and 1 as a column matrix. Okay, so now let's get C underscore X. So as I've explained, the elements is going to be 2, 2, minus 1, 13 minus 1, minus 3, 1, 3, minus 2. So you could construct this inside a note so that you are able to visualize it and you know what the elements are supposed to be like. It's going to be easier if you can visualize it before now giving it to MATLAB the way MATLAB understands it. Okay, so let's move to creating C underscore Y. So the members are 3, 2, minus 1, 2, 1, okay, 2, 13, minus 3, 1, 1, minus 2. And the third matrix that is to be created, C underscore Z, the members are going to be 3, 2, 2, 2, minus 1, 13, 1, 3, 1. Okay, so let's see where the error is coming from. Okay, there's supposed to be space between, in the second row, between 2 and minus 1. So we have that. So the next thing is to find the determinant of this newly created matrix and divide it with the determinant of the coefficient matrix originally from the three linear equations that were given to us. So for x, the solution to x is going to be the determinant. You call it function determinant and supply the argument. So the argument here is C underscore x, now divided by the determinant of v. So this should give us the value for x. So x equals to 1. So let's move on to getting the value of y. So y equals to minus 2. Let's move on to getting the value of z. Okay, the value of z is minus 3. Okay, so for the set of linear equations that we had solved using the inverse function and the backslash, I would like you to try your hands on it again as displayed on the screen now, using the Cramer's rule, which involves getting the determinants of some of the variables, some of the matrices that will be generated, and you solve. So I expect that your answer will be the same as we got when we use the backslash and when we use the inverse function. So now we move to another another topic that I titled data visualization and interpretation. So let me clear my workspace and my screen so we can start on a clean slate. Okay, data can be generated from functions and you can acquire it from experiment. So you can import data from external context into the MATLAB workspace. Either it's generated by function from other software or you acquire the data experimentally. You can use them in the MATLAB workspace by importing them into MATLAB workspace. Okay, so like we have seen in the previous classes that we have had, you can load your data into the workspace by using the load command. So let's say, for example, we had saved some of the variables that we have created in the previous sessions. We have saved them and now we want to work on them further. We can load them to the workspace using the load command and work on them. And also, like I've said, we can import the data. So let's say, for example, I need to import some data. I can go to the import icon as seen here, click on it, so it's telling me now to go to the location where the file that I have my data is. So I have a data, very small data, on my desktop and I've saved it into an Excel file called students. So let me select it and open it. While the data I have there is small, let me show you how it looks like. Let me show you what's in there. So while we wait for it to load, this is the data set. So there are just two columns in that file. The first column header is age, the second column header is income, and there are three numeric data in each of the rows under each column. So while that data is small, you could have a large data set, maybe running to thousands of columns, thousands of rows. So it's still the same way that we are working on this file, that you could work on those files. So this is the content. It has opened up. This is the content. So we know what is actually in there by the time we load the file or import the file to Excel, to MATLAB rather. So now it has been loaded here. So the next thing is I want to select the data that I want on my workspace. So I need everything. So I ensure that all that I need is selected. Once they are selected, then I will click on import selection. So now you see that on the workspace, the file is now showing students, and it's a 4x2 table. It's a 4x2 table. So I can close this now since I'm done importing. Okay. So how do I get the data that I need from this table that has just imported? The first thing is that you need to know what are the columns that are available in that file. That's one of the reasons I've shown you the file. You see that we have the column age, we have the column income. Age starts with small letter in that file, and income also starts with small letter in that file. So the next thing is that you must be very sure of the name of the file. The name of the file here is students, starting with capital letter S. So we can fetch, let's say for example, the data inside or in the column that is tagged age. We can fetch it by using a command similar to this. So we are specifying that we need every data set starting from the second row up to the last row. You can determine up to what extent you need the data, but why we are starting at 2 is because the first row is the column tag and the data set actually begins from the second row. Okay, so and you could even save this into a variable. So let's save it into a variable called age, and let's see what happens. So we have our variable age created, which is the data that we need. So if you have thousands of data set in your file, instead of you typing it one at a time again, you can just use this technique to extract exactly what you need from that file. So we can create another variable. Let's call this time around, let's call it income, as contained in that file. So I'm going to replace age with income. So it's still going to start from the second row to the last row under that particular column income. So let's see what we have there. So it has given us, it has created a variable income that has the data set that we actually want. So that's the way to get your file and get the data that is therein, and from there you can begin to work on it as you intend. Now there's another way to it. Now let's look at our current folder. It's possible that from underneath you could have added your file into the current folder. If you have it in your current folder, then there's another approach to getting the data that you actually need from that file. So the first thing is that you need to know what is your current folder. So if you look here, you see that my current folder is MATLAB, and that MATLAB folder is in my document, and that document is in my computer. So I can go to the back side or the back hood or underneath the hood to put that same file in this folder so that it now appears in the current folder. So let's do that. Okay, so I have a copy here. Let me just cut it and position it in this folder so that by the time I go back to my MATLAB interface, that particular file will be there. But before I go back, remember some classes back we did created some scripts, and we see how we can publish those scripts so that you could share your code and the solutions that you have obtained with people. And when we published the script, a folder was added to our current folder, and this was the folder named HTML by MATLAB itself. So if you double click it, you can get the file that you created by publishing. When you publish, you specify the type of file that you are looking for. I specified document, so that's why I'm saying document, and I named it today. So if I actually need it, I can come to where my MATLAB folder is actually located on my computer and get it, copy it out, and share with those I need to share with. So that's just by the way. So let's go back to our lecture. So now let's go back to the interface that you are working with the MATLAB interface. So now you see that the student file is now showing in the current interface. So how can we work with this? First, let me clear the variables that we have created before, okay, and let me clear the command space, the command window. Okay, so we have a clean slate again. So now that we have our file of interest on the current folder, we can use the function read matrix to make the data inside that file behave like a matrix. So what we just need to do is to call the function read matrix, open the parentheses, and supply the name of the file that we want to handle as a matrix. Okay, in doing that, we can store it inside a variable. You name that variable a name of your choice, something that is meaningful enough to guide you. So for this purpose of this class, I want to read the data inside student.xls into a variable called data. So using this command, okay, so we need to be careful when we copy from text interface to MATLAB so that the quotation marks is actually what it ought to be. Okay, so notice that before I press enter, my workspace is actually empty. So now that I press enter, let's see what happens. So it has now created a variable for me called data. So how can I view the content of data? I will just type data and press enter. So I see what is in there. So it's the value that we have seen that is in our students.xlsx file, but the header, which are text, have been removed, so it only brought out the numeric data for us. So now that we have our data and it's like a matrix, we can extract the part of the data set that we need. So let's say this is running to thousands and you don't actually need everything, you know where you need from it, so you can extract the part that you need. So this is us applying what we have learned in the past two classes on extraction of a submatrix from a matrix. So let's say, for example, we want to create let's say a variable that excludes the first row. So what we just need to do is to say we are extracting from data, we open a parenthesis, so we are excluding the first row. So that means we are looking at row 2 to row 3. Row 3 is the last one in this case, so we can say row 2 to end, right? So that's the row. And when we are talking about matrix, we need to specify the row followed by the column, and this is separated by a comma. So we say row 2 to end, or someone might say row 2 to 3, comma. We are interested in all of the columns. So how do we indicate that? We said that if we need all of the data in a particular range, we just use column symbol. So that means for this column size, we are saying we need all. So this should generate element 17, 44, 20, 70 for us. 17, 44 in the first row, 20, 70 in the next row. So let's see the outcome. Yeah, it has expected. So similarly to the way we stored the data for age inside a variable age and the data for income inside the variable income, we can also do that on the matrix data that we have created. So we have a matrix that is called data, and we want to store the data for age inside a variable age. So we create a variable age, we say equals to. Now we are extracting the data for age from a matrix. So we name that matrix, we open the parentheses, and we extract what we need using the technique for extracting a submatrix from matrix as we have done in the past. So the data for age is in the first column of matrix data, and we are extracting everything, every row in that first column. So we are looking at everything, every row in the first column. So how might we do that? So we specify the row. What rows are we looking at? All of the rows. So to say all of the rows, we just say column. We use column to depict that. So we have specified the rows. Then the next thing is specify the column. So we put the comma and say what column are we looking at? We are looking at getting column 1 alone. So we put 1. So we press enter and see the outcome. So we have our age, the data for age stored inside age. So we can replicate that for the other variable, which is income. So it's going to be income. This time around, we are looking at the second column because that is where the data for income is, and we are taking everything in that row in the second column. So we can still use column to depict what we want to do, what we want to copy. Somebody might say, okay, instead of using column, somebody might say 1, 2, 3. Since we have 3 rows, it's still going to yield result. But let me follow this route, and I have this. So those are the ways to get your data, the needed data, from an external file. Either the data was gotten experimentally or generated from functions. So you still use it in MATLAB, extract them to the workspace and work with them. So we continue from here the next class. Thank you.